Okay, class. So finally, here. We are. After all the introduction on principle of virtual work, theory of infinitesimal string to tell you how to do displacement function into string and then stress. We're finally at the point we're gonna actually use it, and then we're gonna present our case example with no other than the simplest thing possible. That is a bar. Okay, and then apparently we're gonna just put bar in the most convenient location we can, and then we have this I and J. Yeah, we're starting to go with our matrix setup. We have A, E, that's a constant, then the length is L. So basically what we're doing is that we're gonna apply a force which is a real force, Fi and Fj to this bar, and then this bar is gonna move a little bit, and then you're gonna move into the deformed configuration, which we will say this is your true displacement Ui, and then this is your true displacement. Everything's true. There's nothing virtual about it. Uj, okay. And then guess what? We're gonna to do principle of virtual work. We're gonna impose a not true, which is virtual displacement. So it's gonna be I'm gonna all the way. This can be your virtual uj, and apparently this will be your virtual ui, and those guys are virtual. They can be anything. This is real. Okay, it's gonna have real force, real displacement, real string, and then inside it it'll have some real stress. So we want to establish a relationship between those two guys and those two guys. So how do we do that? We need to kind of if you go back a couple of lectures, when we first introduced principle of virtual work, how to calculate the internal virtual work, we say internal virtual work for a bar that is actually it has to be uniform, which means the cross section will not change. But then you're like, oh, how about it changes? Oh, it changes. You just cut into smaller pieces. Or we can show you later, if it changes, the A will have to be a function of x, and we can integrate it as well. So nothing too bad, just mass. So yeah, we know this is over V of real stress and virtual string dV, but for a bar it can be simplified as, if you have a displacement function, it is A times E times 0 to L, and then d u dx times d virtual u dx. So if you don't know where this came from, just go back to your notes. Okay, a couple of lectures behind. So yeah, with those as a kind of background, let's see what we're gonna do with it. Okay, we're gonna just apply the principle of virtual work, which simply says, yeah, it's 0 equals to all total work, or sometimes we can just do external work virtual equals to internal work virtual. Okay, so we just need to just write out each one of them. So the external work, this one's actually quite simple, because you know what, that's a real force, external, doing work on virtual displacement. So we have two real forces. So we have a Fi, well, that is real, and then doing work on virtual displacement, which is delta Ui, and then we have another force doing work. So yeah, you got that. Yeah, that's it. I mean, there are any other forces external? No, nothing, no other external works for this element. But everybody has basic physics education, you know this is right, but when you calculate the work done by force, we're going to write it in a different way. We're going to write it in fact, that we're going to just do the virtual ui and uj. I'm doing the virtual on the, so that I don't have to write it twice. Okay, times your force vector fi fj. I mean, if you look at this notation, like this thing, if you do the shovel rule, it's exactly the same thing here. So nothing, I haven't changed nothing, but write it in a kind of force vector form. Okay, the real beauty comes into a writing of internal virtual work. Okay, so we'll see. Okay, let's take a look. Okay. If we follow this, we know A, we know E, it's given here. We know the integral limits L, but we need to do this. And we have to realize that just one lecture back, this is displacement function, which is, you know, on the back end here. If you recall, the displacement function of a bar, we write it as n, we'll say ni, and then which is a function of x, okay, and the nj, which is a function of x. I think in the past lecture I do n1 and n2. Yeah, you know, it's the same. So times, if it's a real displacement, I'm just gonna do ui and uj. That's gonna be real, okay. But if it's virtual, those two won't change because we're gonna use the same format. And times, now all I need to do is just do virtual ui uj. Okay. So now you see the beauty of this. I mean, this thing never changes, the shape functions. So let's actually apply this. So it looks like we're going to take a differentiation of this guy and this guy. You're like, oh, how am I going to do that? Remember, although I write this in a matrix form, this is just like this guy times this guy plus this guy times this guy. That's it. It's a simple formula. And when you take a differentiation, those are constant, so they won't take any differentiation. The only thing they're going to take differentiation is the function with respect to x. So, so you got this differentiation of this guy equals to dni dx, and then dnj dx, then times, yeah, those things will never change. So the same thing is happening here. I'm not going to write it because, you know what, writing like this, like d, I, whatever, it's very, yeah, because can you imagine how many times I have to write it during derivation? I don't want to write it all the time, so I'm gonna kind of give it another name. I'm gonna call it bi. So bi is also a function of x. It's basically whatever the shape function of I node is, take derivative of x. Apparently this will become bj. So in fact, if I have this notation, the writing of differentiation of the virtual is very simple. It's just a bi bj times you know, virtual ui uj. Okay, got it. Okay, now once we have this, let's see what we can do here. So the internal work, if you kind of think about how this is done, is essentially I'm doing nothing, I'm just copying the formula right here, and I'm gonna plug in this. So basically it should be the bi bj then times ui uj. This is a real string. Okay, this whole thing times then I'm gonna do bi bj, but now I'm gonna times the virtual displacement. Okay, and then this entire thing, then I'm gonna do the dx. Then you're like how, oh gee, like, oh, this is like a disaster. But you know, in the end, if you just look through it, this is just a number. This is just a polynomial. Yeah, not polynomial, but it is polynomial for this case. It's just a function times another function of x, then doing derivative, doing integral of x. Because those functions are all together, in fact, I can actually do this dx at every individual components. But if you want to write it in a pretty nice way, you know, I have a lot of parentheses. This is a little crazy. And then if you do a little bit of matrix operation mass, which is nothing fancy, you get something like this. You get AE. In fact, I can get rid of all those parentheses by just manipulating how I you know, rotate my vectors to be something like this. The virtual guy is gonna come here, and then it becomes a row vector. Then we will times the bi bj as a column vector, then times bi bj as a row vector, then finally times ui and uj and dx. Then you're like, how can you go from here to here? I mean, if you just do the matrix operation thing, and then you find out it works. Okay, it's just some simple math. So what we're gonna do here is we're gonna actually realize that these guys are constant. I mean, they can be anything, but they are constant to x. They don't change with respect to x. Those guys are constant. Yes, for some reason. The only thing that are function of x are those guys. Functions of x. So the integral, you can take those guys out. The constant you can go out, and then you only do the integral on the actual functional part. And then at the same time, I'm gonna kind of rearrange terms a little bit, then to make it a little bit more easy. Times this entire thing, which is a e 0 to l, and then I'm gonna actually, you know, time them together. So basically, it becomes bi square, then bi times bj, then bj times bi, then bj square. It's became a matrix. Yeah, because I mean this guy times this guy is became a matrix. Then I'm gonna do dx, and then after this entire thing, I'm gonna do times the ui uj. Okay. Now we got this figured out. We just need to apply the principle of virtual work. Let this one equals this one. Then you're like, what's this one? It's right here. Okay. I now need you to pay like really close attention to the formulation here. We got this part here times this vector equals to this part here times a matrix times this vector here. And this guy and this guy can be anything. It doesn't matter. So in order for principal virtual work to always work, this guy has to be equals to those two guys times together. And then by definition, whatever is here connects the real displacement vector to the real force vector. So this is our EK. Okay, wow, you're like, this is crazy, right? So basically what you're saying is that for a bar of AE and L, I just need to put AE there, and then I need to take my shape function of I and j, I differentiate them to get up my B, whatever that is. Then we're gonna put B into this matrix so that each component of the matrix is actually a function of x. And then I'm gonna integrate those B's from 0 to L, and then I got my EK. How do I integrate a matrix? Oh yeah, I mean, if you have a matrix that has each component as a function of something that you want to integrate, you just do each component one by one. Okay, so there's just a lot of work, but nothing fancy about that. So we could just say EK of bar simply equals to AE. Then the matrix is like you integrate 0 to L bi square dx, and then integrate 0 to L bi bj dx. The integral of bj bi, which is the same. I mean, you probably figured that out by now. Finally, bj square dx. Okay, well that's cool, but does that work? To figure out if that works or not, we can actually just plug in our shape function of our bar, see if it works. And we all know that. If you don't know, then just go back to my notes. The ni is actually equal to 1 minus x over L. The nj in this case equals to x over L. Yes, do remember, this guy is actually this function. This guy is actually this function. Yeah. If you don't know what I mean here, you really need to review. Okay. So if you do take differentiation, then what do you got? That bi. Bi is actually take differentiate of x is negative L over 1 over L, and bj is take differentiation is L over 1 over L. So let's just do this. EK equals to AE, and then you got this 0 to L, and then you do this guy square, so it's square dx. You're like, hey, hold on, you said b is a function of x, right? But there's no x. Yeah, I mean, because the shape function here is linear. You take one differentiation, then it goes away. So yeah, surprise. But later when we do beam, we're gonna do it in the next segment. The b is not gonna be constant anymore. But yeah, you got it easy this time. It's constant, and then you do this guy, it becomes negative L squared dx, and then you got the idea. And finally, bj is not that different. If you really do the integral, it becomes x, and let's just do one like dx equals to so basically L it becomes x. This evaluated between L and 0, then becomes like you plug in 0, there's nothing. You plug in that, it's L over 1. Okay, so it becomes L over 1, negative L over 1, L over 1, and negative L over 1. Then you got the L over 1 over L over 1, 1 over what is it? Whatever. You got the 1 over L out. You got A E over L, and then 1 1 negative 1 negative 1. Okay, that checks with our results we got from mechanics and materials. But if you look at this, gee, we didn't do anything about mechanics and materials, right? All we did is just follow principle of virtual work, and we have a pretty consistent shape function figured out, and then we just do this, figure out how to calculate the internal work, plug it in and rearrange terms, and then we get to this, and magically once you plug in the displacement functions, it works. Okay, this is to kind of introduce you into the concept, so I'm going pretty slow here. Next one, we're going to do beam. Okay, we're going to do beam, and it's going to be a little bit faster. So we'll see you next time.